So before doing some calculations which reduce in, I think I will give you the lecture notes, which reduce to 4 pages the calculations of more than 40 pages by Piola. I have to explain you how this miraculous reduction is possible. And this miraculous reduction is possible because we have in our hands a powerful tool which allows us to express in an easy way the invariance of deformation energy under change of observer. So if you have a body which is being deformed, okay, and if you consider 2 observers which measure what is happening to this body, it is obvious to state that the deformation energy needed to place in a given deformed shape your body is independent of the observer. Okay? So the technical problem which we have now is how to express this in formulas. Okay? So I started proving an exercise which I left you. I hope that if you have not done it yet, you will do soon. So I need to express in components the transposed of a given linear function. So the definition is here. You first calculate the image of the vector capital V. Then you calculate the inner product in the space, Eulerian space. Or you calculate the image of the transposed of small w, and then you calculate the inner product with capital V. So this formula makes it explicit. Transposed is going back. So if L maps capital vectors into small vector, the transposed maps small vector into capital vector. It is deadly to learn by heart the simplification which is killing the substance, that the transposed is the matrix in which you change rows and columns, because you are soon lost with these 2 particular definition, because this definition makes sense if you have an application in from one space to itself. Maybe. Okay. So what is important is that you understand that the transposed is pulling back. So if L is going forward, L transpose is pulling back. Now, using this equality has to be true for every capital V and small w, which we have written here. So I write everything in components. So I have GAB, which is the Riemannian inner product matrix, WB, which is saturated, and the image of L. So you have the free index A, which you are saturating here, and the capital A index, which is saturated there. So this is the vector with small index, image of L, and this is the vector W. Okay? So I have simply written in components this quantity. Okay? Then remark, this is the really clever trick of this notation. I should write another symbol here, but as I use capital indices, this is useless, because you understand that you're talking about the inner product in the Lagrangian reference. So you saturate capital VA, and you saturate small b, and you get the free n there. Okay? So this technicality is very easy. Now, what you have to do? You have to take this on the left, equal 0. Factorize WB and VA. This animal, which you get as a factor of WB and VA, must vanish, because the saturation for every W and V equals 0. And after few simple calculations, you get that the transpose of L has as a component small I capital L, exactly LIL. But what you have to consider is the following. This animal is saturating small indices, while this animal is saturating capital indices. So when you calculate LA VA, forgetting the image, you saturate the capital index, while when you apply this, you are saturating the small index. So this animal is giving you the switched.
Is that correct?
Yes, this is correct. In order to get L transposed NB, you need to calculate GNL of L transposed IL. As in general, this tensor is diagonal, and it is always a Kronecker delta, okay? Then you don't see the difference, okay? But actually, in this formalism, you understand that the transposed is not directly. What means transposing two indices which are completely different? It means nothing. So then you replace this animal here, and you get the representation of the right B, I mean the one-time contravariant, one-time covariant representation of L transposed with the covariant index which is needed, so small one, in terms of the similar representation of L which is given in terms of this animal. Okay? This is very delicate. This is a very delicate issue. What we will do next cannot be understood if you don't understand this. So the technical ideas you need, I repeat, are the following. First of all, you have an inner product. Remember, this makes evident. This formula makes what I'm telling you evident. The transposition depends on the matrix. If you change the Riemannian matrix, so if you change the inner product in the departing and arrival vector spaces, you change the transposition operation, which is clear from this definition. So this formula tells you that the transposed depends on the inner product. Okay? Now, remember always this definition, which is very important. When you have Riemannian inner product, then the matrix corresponding to the 2 times covariant Riemannian representation, so the 2 times contravariant representation of the Riemannian bilinear form is the inverse of G, as this formula makes explicit. Okay, the poor Piola needed 5 pages for understanding how to change the covariant to the contravariant components, because he calculated the adjoint matrix for a 3 by 3 matrix, and then he proved that the row times column product gives the determinant of the matrix in the diagonal and 0 out of the diagonal. So all this becomes very painful if you don't have the correct formalism. Okay, next step. Next step is here. With some pain, we have discussed in a previous lecture that the right way for measuring deformation is considering F transposed F, which is very elegant, because you take a vector V, you apply F, you get a small vector, a vector Eulerian. Then you apply F transposed, and you have back a Lagrangian vector. Okay, this animal, if the determinant of F is positive, this animal, this C, produces a new inner product in the Lagrangian configuration, because you can do C applied to V, comma W, the initial inner product TB. Okay? This is definite positive. So you can say what I told you already. You can say that the most clever way for measuring deformation in a given point is to introduce a new inner product, which is the inner product related to deformation. Okay? Now, this C is automatically independent of the observer. Why? Consider the reference configuration. Then you have the placement, the actual configuration. You have one observer, or you have a second observer. The deformation gradient F is the composition of the gradient of key and the gradient of the passage from one observer with respect to the other. But we have studied carefully this change of observer. It is a linear map. This linear map is represented by an orthogonal matrix. So if you have the observer one is measuring F1. You have the observer 2 is measuring QF1. So the gradient of key as calculated by the second observer is F2, and the gradient of key as measured by the first observer is F1, and the two gradients are related in this form. Okay? Now, consider here, if I replace to F2, so if I write C2 is equal to F2 transposed F2. This is equal to F1 Q transposed Q F1, F1 transposed equal C1. Okay? So this quantity, this inner product in the Lagrangian configuration is independent of the observer. Okay? So you have the tool for doing what you need. You will ask to your deformation energy to depend on C. If you have that your deformation energy depends on C only, then you are automatically assured that this deformation energy is independent of the observer. Okay, this idea has been developed painfully after Piola. So this you don't find in Piola. In Piola you find complicated analysis for getting interesting results. Actually is introducing remark that I can tell that C is symmetric because it is a map of one vector space into itself. So given a basis, there are only 6 independent components of C. Piola calls them T1, T2, T3, T6. Okay? But is discussing that this T is independent of the observer, and he writes the deformation energy only in terms of these T6 components. But there is no general analysis as done subsequently by Green, then Kossera brothers, and finally by the experts in elasticity like Poincaré and Einstein. Most like Maxwell also played a role here. So all this treatment is the final result of a series of considerations which lasted at least 60 years and were made possible by Levi-Civita tensor calculus. Okay? Now, I need to represent C in a given reference. So I write CMN equal, I have to consider F transposed F. Okay? So I saturate the small I, because it is not appearing anymore, and I need 2 contravariant indices. So I write it in this way. You can check easily from, this is equal to say FW, FV. Okay, so you replace F inside or F transposed. It is exactly the same reasoning I did before. This is one possible representation of deformation measure C. By the way, this is called Cauchy-Green deformation, but in recent times, in books they call it green only, because Cauchy, in a sense, was taking it. So when you consider F, you have to saturate it with the metric tensor, and this is C. So this gives even a more evident proof that the new C is an inner product which is different from G, and it depends on the deformation gradient. Okay? Why I need this explicit expression? I need this explicit formula because soon I will need to calculate dCmn over dFIL. This technicality I will need soon. So I prefer to do the calculation before, and then I will not be obliged to stop my variational argument to prove a technical result on the side. On the other hand, without this technical result, the variational argument I'm showing you is not possible, or it is possible with the painful calculations by Piola. So this blackboard is saving us, not only this blackboard, the effort of abstraction which is behind this new formalism, together with this blackboard, allows us to save several pages of calculations. So I have written this. This is constant, so it goes out, the derivative. And then I have to calculate the derivative of this product. This is very easy calculation if you are inside the formalism, because the derivative of the product can be calculated with Leibniz formula. One should not forget that these two are two scalar quantities now. So you treat them as standard variables. So you get dFBM dFIL times not derived FAN plus the first one not derived times the derivative of the second. Now, as the blackboard is small, I have directly written the second derivative. So you understand quickly what we are doing. Of course, you have a variable with two labels, and you derive it with the same variable with, you have a family of variables with two indices, and you derive the generic member of this family of variables with respect to a fixed one. So this derivative is 0 if the two are different, and it is 1 if the two are equal. So imagine the poor Piola who had called this F A, B, C, D, A, F, G, H, E, 9 elements. Then he painfully discovers that in C you have only 6, and here I have calculated in one line 9 derivatives, because I should write dA over dA equal 1, dA over dB equal 0, dA over dC equal 0, and so on. Okay? So with this formalism, I quickly get the final result, which I write here, because we will need it soon. The final result is the following one. dCmn over d FIL is equal to delta LM FIN plus FIM delta LN. This derivative we will need soon, so we keep on a side. Okay? Now, our periodic medicine of tensor calculus is for the moment enough, and so we go back to our general action functional. So I want to underline here that this is the only moment in which our modeling procedure is inventing, is conjecturing something. So I claim that my deformable body is moving, minimizing the following action, which I now write. You are not allowed to ask why. This is a meaningless question. You conjecture this, you solve all your problems, you forecast some behavior. If after many measurements you get good results, then you claim that your theory is predictive. So you can forecast enough. Okay? This is written in a book of Archimedes called On the Method. So, action functional equal integral between T0 and T final. Integral over the body B of 1/2 rho 0 V square minus W of key F and capital X dV dt plus integral on the boundary of B of minus W S K capital X d area dt. Okay? So let us discuss what this means. Key I already introduced for you. F is the gradient of key. Your body in general can be not homogeneous. So in different points you may have different properties. So in general you have this dependence on capital X. This rho 0 is the Lagrangian mass density. So this animal may be a function of capital X, but it is not in general depending on time, unless you are studying a rocket or a mass varying object like a bone. But the theory becomes much more complicated if mass density can vary. Okay. V we have already introduced, but I recall you that V is d key over dt with x fixed. Okay? So this is the partial derivative of key with respect to time being capital X fixed. Okay? So this is the standard velocity of the material particle capital X. Remark that this B is fixed in time. This is the Lagrangian configuration of your body. So it is not varying in time. Okay, so this is the typical Lagrangian action for, actually we can say that the theory, this action includes the theory of, no, this action coincides with the theory of deformable first gradient continua. It is a continuous system, and it is a first gradient simply because here you have only the first gradient of key. Okay, I state, and I will prove, that all equations used in engineering applications, except very few, are included in this theory. I think that we can talk about the Cauchy straitjacket. The straitjacket is the jacket you use for not allowing to crazy people to move their arms. Okay, for a reason, engineers accepted the Cauchy straitjacket. So they cannot think anything outside this model, which is very dangerous. Seneca would behave like that. You know, it is typical of a given degenerated time when people mixed the model with the reality. Then, instead of considering the epicycles which are used for building machines, which are used for calculating orbits, you start believing that in the heavens there are wheels which are turning. This is the typical misunderstanding. You misunderstand reality with the model. Okay, so this is a model which is not working for drops, for evaporation of a drop. Okay, so you have to change it if you want to describe drops. Okay. Now, a formula which we will not need immediately, but it is clear, is this one. The mass density in the actual configuration is equal to the determinant of F minus 1 times rho 0. This is a kinematic condition which is included in the theorem of change of variables in the integrals, which is standard. Okay? Now, should we do calculations? Why? Why should we do some integration by parts? We calculated the first variation of a much more general functional in the last lecture. So we simply apply the result we have found. This is a four-dimensional space, so you have a variable time, three-variable space. The derivative, so for instance, you can remark this. F is the derivative of key with respect to space. V is the derivative of key with respect to time. So V and F all together are constructing the four-dimensional gradient of key. This is the source of every difficulty. If in fluid dynamics you forget that rho is related to the determinant of F, which is the gradient of key, and that V is the derivative with respect to time of the same function, you are lost. Because if you give a scalar field ρ and a vector field v in general, such a key is not in general existing. Behind everything there is a motion. Okay, so this is what is fundamental. Okay, now this is called kinetic energy, and it was conceived in modern times, at least by Descartes somehow. And this we can call deformation energy and potential energy. Inside this W you have many things. You have the potential energy related to deformation, but you also have the potential energy which one particle is experiencing in a gravitational field. I mean, here you have both internal and external interactions. Here you have all deformation energy, all interaction energy. You have all the energy which is attributed to your system. On the boundary of your body, you also assume to have a potential. So you have an interaction with the external world, okay, which is represented by this WKX. Okay? Now,
can I ask you a question about?
Yes.
I was wondering that minus sign over there.
Kinetic energy minus potential energy.
That's clear. I mean, from the general point of view. No, if you interpret that as the gradient, space-time gradient of chi, so you have, assume you have a W which is quadratic in F, so you have F transpose F for instance.
Yeah.
V square is the same thing in time, so it's quadratic in the time component of the gradient. Why this asymmetry arises between time and space? You get the minus there.
You are talking about the okay, I could in an erudite way talk about the theorem of living forces. Actually, the idea is the following, is that inertia is subtracting energy to the deformation energy or to the potential energy. This minus here is related to the different role which inertia and potential energy have.
This is clear from let's call the physical point of view. I was wondering why this symmetry is sort of lost.
This is
otherwise the theory is completely. You cannot distinguish time from space unless from the fact that you have a general W instead of a simple quadratic term in the.
Okay, Carlo. Indeed, expert in rational mechanics. And instead of calling this potential energy, call it the potential.
But
then in the equations you will get some signs which are jumping in another way.
Okay, but I need a need. Now, in any case, I mean the energy would be F transpose F in the simplest case, 1/2 maybe.
Yes, but you have a sign which is changing in the potential energy.
But still, I'm not sure what I'm saying, but still you have the chi dt square, which is v square,
yeah,
with a plus, and then you will have, for instance, the chi 1 dx1 square with the minus.
Yeah.
So, I mean, the asymmetry is built in.
The asymmetry is built because some variables, independent variables, are space type, and some are related to the evolution. So my first answer is still valid, in the sense But in any case, we are talking about the result of many pages of calculations, because this is a conjecture, and the violent controversy about the so-called theorem of living forces was exactly caused by the fact that somebody wanted different signs there. So, I mean, we are here reproducing an ancient discussion, and at the end of this ancient discussion, simply, we must conclude that inertia is such a strange animal that you need a different sign there if you want to talk about conservation.
Okay, but this sort of means that if you express them in four-dimensional space, then the signature of your matrix is like something you have.
No, the signature is always the right one, but the boundary conditions are different. Because, okay, but this is too much for. No, but I answer you because.
I will answer later.
No, I answer you now, then we go back later. When you integrate by parts this animal, you will distinguish two kinds of boundaries. The space-type boundary, where you have a boundary conditions involving the gradients of this animal, the gradients of this animal, and that's it. Then you will have another kind of boundary, which is time kind boundary, in which you give initial placement and initial derivative of placement, so initial velocity. So this gives you a difference between F and V. You give initial V, you don't give an initial F, in a sense, on the boundary. On the boundary. So there is a world of hyperbolic, parabolic, elliptic equations, classification, and things like that. So we say this for the records, then maybe we'll go back at the end on this. Okay, so if you remember the general equation which we wrote, it particularizes in this. Here you have minus, because you integrate by parts in time and you get minus there. Here, what you have to add inside, the derivative of the Lagrangian with respect to velocity. So, rho 0 v. Okay? Then, now you have plus because of this animal. Okay? Because the divergence we have calculated is without, the inner product was with all plus. So you get a divergence with all plus. Okay? Here you have plus d over d capital X C of what? dw over df IA minus dw over dk equals 0. Okay, I place here I and here I. Okay? So, even if there is a long habit of repeating in different courses exactly the same calculations, okay? So you prove divergence theorem and you apply it 1,000 times, you changing in a crazy way notations and everything. We try to unify, okay? So this is a particular functional of the kind we have studied. It is very simple functional because you have only one field, key I. You have only one vector field. The first variation, which we have calculated already, gives you this evolution equation. Okay? This is what is called balance of force or balance of linear momentum in continuum mechanics. This animal is the source of force. As here you have a flux, a divergence. You can interpret this animal as a flux of linear momentum or force, and this is inertia. Okay? Well, this is very trivial. You calculate the first variation of this, you get this. And this is valid in general. Now, you remember that W, for being objective, has to be split in two parts. You have the potential energy of interaction with the external world plus the deformation energy. So this is very elegant. You start from one assumption, then you add one after the other the needed assumptions, and you produce the equations you are looking for. So now what I'm doing, I am introducing W equal W deformation, which is a function of C and capital X, plus U external, which is function of K and capital X. So we were very general. Our model was too general because it could be dependent on the observer. Okay. Now what you are doing is you are splitting your potential energy in two parts in an additive way. Of course, there are many other possibilities, and you could invent new models in which this decomposition is not valid. And indeed, sometimes this is done. Okay. So you say, I have inertia, kinetic energy. Then I have a part of potential energy which is of the form of deformation energy, which depends on deformation green measure C, and a part of energy, potential energy, which depends on the interaction between your material particle, capital X, with the exterior world. Of course, if this animal depends only on capital X and does not depend on key, you have very particular loads which may be of some interest. The actual important dead load is on the boundary, where you have no dependence on key. Okay? So in general, you have a material particle labeled with capital X. You have where it is placed, and you need to know which is its potential energy in its interaction with the external world. So you have an external world which is interacting with every material particle of your system whenever it is placed, and you need to know this function. So in a sense, if you like, you are giving some constitutive equations describing the interaction with the external world and the way in which this body is deformed.
Let me try to see if, when you split the energy, deformation and external one, and you take the deformation to depend only on C, you imply that this is the only way you can have objectivity from that?
It is painful to prove. I didn't want to tell it. Okay, yes, but it is not so easy. You need theorems of representation. You can ask you, given a scalar quantity depending on f, which is the most general function which is observer independent. I have proven to you before that if you choose C, it is independent. You can also prove the opposite. You need Schur lemma, you need Lie group theory. I mean, it is not easy. There are some easy representation formulas. Actually, you need to know which are the isotropic functions of scalar functions of tensor variables.
Right. Yeah. So that can be checked. You cannot have chi inside the deformation.
No. No.
This could be interesting to
But you can have grad C. You can have grad N C.
The N gradient.
Because all of them are objective.
I think this would be nice. You don't think you can include at least some basics about it? I mean,
You want this theorem?
I think this is important.
Yes, it is important. It is important because the same theorem allows you to say that Stokes-Navier stress depends in that particular way on the grad V.
Yeah.
Okay, one should explain to many fluid mechanicians that the theorem allowing you to represent isotropic deformation energies applied in solid mechanics is the same theorem used for Stokes-Navier equation, but you know they don't. Some of them cannot understand because fluids are different from solids. So what you want? So the crucial point is this one. It is a good maybe. It is good to tell it now. So I will include in my future presentation. This is the only way for getting objective deformation energies in terms of only C. If you include higher gradients of F in the picture, then you have also higher gradients of C. To prove this is not easy. I can organize 2 lectures for proving this. Okay? Good, but then the medicine of tensor calculus will be 2 bottles more because it is more complicated. Okay, now, if you remember that when you are calculating partial derivatives, key F are independent variables, as we said many times in the last lecture, this formula is transformed in this one. Because dW over dF depends only on this term, because this animal do not depend on F. By the way, this can be relaxed. You could have external action, and this happens in pneumatic fluids, many kind of dielectric materials, in which the external world is acting on F. Okay? This animal, there is no dependence on Ux, do not depend on F, then its derivative is 0. Okay, so with our formalism we have avoided already many painful calculations, but it is very elegant what we will do now. it is not depending, W def is not depending on F, it is depending on C. So we calculate the derivative of composed functions. So you now understand why I needed the previous calculation. So I write here CAB, dCAB over dFIC. Okay? Okay. Now this passage I could not find even in Coursera Brothers' book. They are not able to identify CAB as the correct variable on which deformation energy must be depend. So I strongly suspect that this is related to Poincaré. Understanding clearly this thing. Just for showing you that I studied some general relativity, the big problem in relativity is that not only CMN is varying, but also the scalar product GAB. So you have another equation which tells you how this inner product is changing. So continuum relativistic mechanics is a very difficult animal, which is used for studying stars or galaxies and so on. Okay, so as we are talking about invariance, we are studying a continuum system, deformable continuum system, which is invariant under Galilean transformations. Okay? By the way, the Lagrangian I wrote to you, if you consider it carefully, it is invariant under translations. Okay? So these equations are, this shows you immediately. If you add a constant velocity, this derivative is 0, because rho 0 is 0, a constant. Okay? Okay, now I replace here what I have calculated before. I am afraid I have to write in another place this anymore. By the way, we are studying our system in large deformation. I never said that C is close to 1 to the identity. Okay? And I'm writing my equations in Lagrangian configuration, which usually is stated to be a very complicated task. Indeed, when I presented my lecture for the competition as associate professor, I was obliged to defend this point of view. Large deformations are easier than small deformations. Large deformations are easier. You understand them more easily. The big problem is to solve nonlinear partial differential equations, not to understand how to formulate them. Okay? Good. So I must write dW def over dCAB over dFIL equal dW def over dCAB, and at the place of this I plug in this animal. So I have delta LA FIB plus FEA delta LB okay. Now you remember that C is symmetric, so a simplification which was not possible is now feasible, so that this and that, remark that the A index is here and the A index is there. The B index is with F and the B index is with delta. So this animal is not one of them. However, as this AB is symmetric, then you can write 2 times, my professor Antonio Di Carlo spoke about the mystery of the 2 appearing in this equation. This mysterious 2, okay, you can place here this formula, okay. Do you know how we can call how we must call of course I can change the index for summation without any problem. Do you know how I must call this animal? This is Piola stress tensor. What is astonishing is that after 40 pages of calculations, he got exactly this animal. So this is the balance. This is the balance of force in Eulerian, in Lagrangian description, invariant for change of observers. So consider this. We have not assumed anything except invariance with respect to the observer and the existence of a deformation energy and an external potential energy. You could say that I don't like kinetic energy and why you use 1/2 rho v square. And indeed, there was a violent discussion about this. Okay, so any question about the structure of this equation can be answered only solving a family of problems and looking how it behaves. So this is the good news is that we built everything which is deforming around us with this equation. So it is rather good one. This is the reason for which many people like this straight jacket, because it leaves you enough space for hands for doing many things. Okay, but if you want to get out of a given amount of phenomena, you cannot get out. I will show you one particular case of this equation for fluids. And when you will see the equation of fluids which you deduce from this, so it is a particular case of this, you discover that fluids cannot exert shear stress in equilibrium, and that a gradient of pressure for fluids is constant. So in this class of materials, fluids have very peculiar properties. If you have a drop of water which is suspended in the air surrounded by vapor, the pressure inside is bigger than the pressure outside, but still they are in equilibrium. So you have two possibilities. Either you behave like Aristotelians and you conclude that world is contradictory, or like healthy Epicureans, you declare this model is not good. I change the model. Now, the contribution of many scientists, starting from Piola himself, and Toupin, Rivlin, Midlin, Casal, Gouin, in the 20th century, is how to modify this scheme in order to include the equilibrium of drops. So, of course, I'm telling you this because I worked on drops, but I want to underline the fact that given a model, there are phenomena which are included. Space shuttle has been designed with these equations. It is a deformable body with heat, okay, but heat flow and so on. But it is the structure of a space shuttle has been designed with these equations. So these equations are very useful. The prosthesis of a leg are designed with these equations. They work very well. But still, there are phenomena which are not predicted in this scheme. Okay, so let's move to boundary conditions. We move to boundary conditions and we discover that dW def over dFIA N A equal minus dWs over dKi. Simply particularizing the equations we deduced in the previous lecture. Now, it is useless that I do calculations, because this animal we have already calculated. So the boundary condition tells you that these boundary conditions are the reason for which people are crazy about these tensors, in a sense. This boundary condition tells you that Piola stress on the boundary of your body balances the external force. Okay? So we will go in detail in this later. Okay, let me see, what time is it? So we will not go in detail now. So we spend some time about this because we have 15 minutes left. We have two problems. You have to understand. Look at this. These are partial differential equations in which you have space and time derivatives. Luckily, the domain is fixed. Thanks God. Okay? It is possible to study shock waves with this formalism, so don't believe that you need a fixed Lagrangian configuration for having variational methods. But so what you have to do, you have to study this PDE with suitable initial conditions. So I can continue to answer you. Consider that this boundary condition has a completely different nature when compared with the initial condition. Because for having a well-posed problem here, you need to add what? Initial key, so the initial form, key at instant 0, plus initial velocity, because here you have a second order time derivative. So this is giving you propagating signals, while this boundary condition is of elliptic type. So the reason for which you have two different treatments of the kinetic energy and the potential energy is fundamentally this. This is the reason for which you treat them differently. Because you want an initial state which is evolving, and you want boundary, space-type boundaries from which you control what happens inside your system. So I added a small detail to the explanation I tried to give before. Now, the big problem we are facing now is how to solve these PDEs. We will see that we can linearize them. I will show you how this can be done. So you find a linearized form of this PDE, and linear partial differential equations can be solved in a closed form sometimes.
Let me ask you a question about this. Once you have set these PDEs, are there general existence uniqueness theorems for this?
I carefully have tried to avoid this. In the linear case, but I answer you. I thought that you were asking me this. I had a meeting lasting 2 weeks in Cisterna where three famous mathematicians came, and we tried to discuss about the present knowledge in this problem. Okay, I tell you that nobody knows very much about the general existence theorem in the nonlinear case. Uniqueness, of course, there is a famous counter-example by Ericsson, but it is old, very well-known story. There is no uniqueness.
No uniqueness even
in nonlinearity and in equilibrium, there is non-uniqueness, for sure.
Euler beam.
But not only.
Euler beam is a steady configuration. You mean given the loads, find the configuration of the steady?
Yeah, there is
but
no.
in evolution, do you think you can have
There is no uniqueness in general. It depends on W. It depends on W.
But is this an issue that you cannot prove it, or there are evidence that you can?
No, nobody knows. Nobody knows. Of course, there are particular existence and uniqueness theorems. What has been done since the very beginning is to linearize this. And then, for instance, the famous equilibrium conditions of Beltrami, the famous Beltrami-Mitchell equations obtained from this linearizing an isotropic or transversally isotropic body. The problem was written in 1856, and the theorem of existence was proven by Figuera in 1960. So they needed 100 years, more or less. Of course, some Russian would say that he proved the theorem before. I mean, but the time interval is as big as this one. But what I want to underline is that for a contingent reason, it was believed that these equations are not good for fluids. When you have a fluid flow Then you have a given pipe, let us call it pipe, a given region of space, in which you know, or better, in which you have a fluid flow which is important for you. Then you can imagine to have an assigned incoming and an assigned outgoing boundary condition in Eulerian configuration, and you can believe that it is very important to transform these equations from Lagrangian to Eulerian description. Why? Because you want to have partial differential equations formulated in your fixed domain. What is written in the Catechism of Mechanics is the following. When you have a solid, the domain which is not time dependent is the Lagrangian one. When you have a fluid, the domain in which the description where you have a not time dependent domain is the Eulerian one. So Poisson pushed Piola to transform these equations from Lagrangian to Eulerian description. You have to consider that you cannot formulate a variational principle in the Eulerian description, easily at least. Because your kinematics is defined in this way, even for fluids. So the right strategy is write these equations, then transform them in the Eulerian description, and then to try to solve them there. Of course, the fact that rho 0 is constant now is very difficult to make explicit. So you need to add so-called balance of mass or continuity equation. So when you abandon Lagrangian description, you need to add another equation. The bad news is that existence and uniqueness theorems for fluid mechanics are very difficult to prove. And there is a reason. When you give ρ and v, so when you give two fields, density and velocity, even if you are relating them with conservation of mass, you are not assured that there is a displacement behind them. This was discovered another time after Piola by Liu in 1960, and it is written in every book of fluid dynamics. So when they try to formulate a variational principle in fluid dynamics, instead of going back to Piola, they introduce strange Lagrange multipliers in the Eulerian configuration. Okay. I want to tell you this. All this work we are doing is important because we understand the mathematical model we are developing. But it became useless for computation aims. The reason is that now computers are minimizing actions. When you write in a weak form your PD, you are minimizing an action plus a dissipation function. Okay? So actually, many times, fluid dynamicists invent fictitious particles which are used to follow the motion of this fluid.
Still not all the fluid dynamicists.
Okay, but very often, okay, this is done. And so, what you have not included in your picture, you are obliged to introduce at the end.
I think that an observation is needed here concerning the fluids. The fact is that with the fluids, the F tensor over there gets very soon approaches the singularity. You get this material line that gets deformed. So this implies that even though in a theoretical setting the F never gets singular, when you do computation, the F gets so close to that you cannot go on integrating that equation.
If you have big compressions.
Yeah, also shear.
Also,
that in a lot.
Yeah, of course.
I think this is the main reason why the fluid mechanics, at least in the computational side of that, is based.
No, this is more general. This is the reason for which we will do next step. We will solve Piola problem. How to transport this equation from Lagrangian description into Eulerian one. So we will be able to use the description which is more suitable when it is more suitable. However, it is, of course, we are not talking about present fluid mechanicians. There are fluid mechanicians who try to ignore completely Lagrange description, which is impossible. How can you define V without Lagrangian description is not clear. Okay? But I mean, this is another story. Okay, so that's it for today.